All right, so today I wanted to talk about, came about by two projects that I was doing internally with NVIDIA. One was working with multi-rail systems and how that relates to MPI performance. And the second one was trying to help tune the NVAP2 stack for use in MPI on a Cray-based system. They kind of came together. This is not intended to be a definitive what has to happen. It was more of the experimentation that I went through. Certainly, DK was showing some charts earlier talking about 2.3a. That has a lot of fixes for performance. I've had some conversations with the med that I'll show something that looks like a bug, and let's just say that was an interesting performance issue that he's pointed out is probably fixed in the next one. So don't take this definitively as this is what you should do. It's a general guideline of things I've done for customers that's better than it was, but there's certainly improvements going on in the stack, and hopefully some of this can feed back into the NVAP2 team, but also show some things that are relevant to architectures that you might see in the future. So we saw this chart yesterday. We talked more about GPU stuff. We don't need to go over it again, but there's multiple components that today are used to improve performance for GPU communications between nodes and inside nodes. The peer-to-peer, the shared memory, and the RDMA are available today. The async is a work in progress. That's not being used, but the other three are in the back end being used for performance for all the numbers that we show. But with all these numbers, if you go and read the man pages, or go read the documentation, which of course we never do, but if you go in all the really good documentation they have for NVAP2, eventually it'll say the parameters are system dependent, and you should tune them for yourself. But when I started looking at those things, and you see a number, let's say the GPUDIRECT receive limit at 128K, to me that first meant, well, maybe it should be 64K, or maybe it should be 256K, or something in between. Not that it should be some drastically different number when you're trying to do your parameter search. And so that kind of opened things up, and that's something I learned from this process, that the settings you need might be far off at this point from where you need to be. I talked a little yesterday about why you'd want to do multi-rail, and I'm going to go over it again. Here are some numbers that we have from a project that we did and created a paper for customers about what's the equivalent performance of GPU to CPU. Now, what we're trying to do here is take standard HPC application codes like Hundi Blue, Spec FM3D, VASP, CUDA. If we ran those on a single node with 8 GPUs, how many nodes of a traditional CPU cluster would we have to build and run on to match the same level of performance? And we really ran these. And we're talking about 30, 40, 50, 78 nodes you need of a CPU to match a GPU node. And the point here is that with all this performance, that's great. We're getting this huge performance benefit from the GPUs. These are actually kind of conservative numbers because when we did the test, we didn't build a 78-node cluster. We built an 8-node cluster, and then we assumed they would scale linearly to be nice to the other results. We know that's not true, but we didn't have the resources to build that sort of CPU cluster internally. So the numbers are kind of conservative. And what this comes out to, we divide by 8 GPUs per each one of these. What you're getting is you're getting maybe a 3 to 10x per performance from a GPU over the CPU node. And that's great. But as I kind of indicated yesterday, that in HPC we scale because we're impatient. We scale because we want to do larger problems. We scale because we want problems to go faster. And just because I'm showing this result of one server with 8 GPUs, the next thing somebody's going to say is, well, how do I scale that and make it go faster? And so you have to consider how you would do that with these MPI applications. And so when we start talking about 20, 30, 50, 80x performance, is a single rail of INFINIBAND, a single rail of OmniPath, going to be enough to suit the needs of the bandwidth necessary for these codes to scale effectively? And I think that you can probably think that maybe the answer is no. We might start also asking ourselves, well, what do we really need? We keep buying these networks. But I think at this kind of level of performance, we know that multi-rail is going to be needed just to support the bandwidth and message rates you need to support application scaling. Here is one number. Be nice to me because I'm quoting HPL. We know the value of that. We ran HPL on 124 quad rail connected DGX1s. So a DGX1 is an 8-way GPU using SXM2 NVLink connected and using a relatively high bin Broadwell processor. It's a 20-core part running at, I think, 2.2 gigahertz base, and it can clock up from there. It's the it's the 2698. So it's almost the highest bin processor. And what we saw running on 124 DGX servers, so that means we have 496 active ports in a 2-layer tree on our cluster that we call Saturn V that we do for our own research projects. We found that by using 2 rails and 4 rails, scaling up, we saw a 20% increase by using the second rail, and then we got up to 40% increase in performance for using all 4 rails. Oh, wow. Questions? Yeah.
Do the rails use separate PCIe links to whatever node they're on? Or are they dual cards that share the same?
So the question was, is it shared ports or are they individual cards? And the question is, I think I didn't put the diagram in here today. They are individual cards. They have individual PCI Express connectors. And those connectors are off of a PCIe switch that is not going through the CPU. So when the GPUs are communicating, it passes through without going to the CPU. It just goes through one switch to another switch to the device. So we can avoid transferring through the CPUs. Other question?
Do you have an idea of what communication got accelerated or what bottleneck got removed when increasing the number of waves?
We didn't look into it further. I don't know the exact answer. I know I've done a little testing looking at applications, looking at like collect all information from the INFINIBAND while running some of these deep learning, or not deep learning, sorry, applications on the architecture. To me, it seemed it was almost bandwidth driven. We weren't maxing out the bandwidth, but I was seeing like 2 gigabytes per second per rail when running some of these applications. So we haven't dug in far enough to understand. Certainly, one thing you get here also is QPI traffic. If we were doing a single rail, you'd have to push things across the QPI. And so there would certainly be a benefit just going from 1 to 2 rails for these architectures and making sure that when I say 2 rails, I'm also saying 1 on one side of the PCI Express, 1 on the other, or 1 on one socket, 1 on the other. It's not 2 individual cards on the same socket because we are trying to avoid the QPI.
Is memory also on the separate sockets? Or
the memory is, we pin things down very tightly. Okay. We go beyond just using MPI stack standards. We have a wrapper script that says exactly, use these 4 cores, and then when the NUMA control is spinning things up, it'll make sure the memory is pinned to the right place. The GPUs are assigned to the ranks and so on and so forth. We even go the next step of, if we believe that the OS is taking up resources on the first core, which sometimes they can be significant when you're doing high-end benchmarking, we'll just ignore core 0, and then when we pin the range of cores you'll give, it will just not use 0 on either socket to allow the operating system to do their thing. So anyway, mileage may vary. Please test your own application. This is HPL. We know what that means. It actually is a representation of deep, dense matrix math, which ironically is coming into vogue with deep learning. But from an HPC standpoint, understand. We have other numbers I couldn't show today that are more like 10%. But it's something to consider as you evaluate your architectures in the future for what things you can do and see how it fits yours. And when you look at this and you figure out the cost, realize that you don't need, let's see, I just looked at this up this morning again, just to confirm myself. It's about $1,800 for the NIC, the ports, and the cables for a 2-layer InfiniBand switch. I mean, you'd have to fill all the ports out, of course, but it's about $1,800 when you look at just micro center or CDW kind of pricing. And if that price, adding onto your node, is less than the amount of performance gain you're going to get, it's a pretty obvious choice that going to multi-rail is going to benefit you, not just in performance, but price performance. So what we did is we took 2 DGXs. They are connected via a switch. They're not back-to-back. The Broadwell part is what I listed. And these tests have been done with MVAPage 2, GDR 2.2. Now there's been a lot of changes for 2.3a. I wasn't using that because the customer that I was also trying to do some separate experiments with, we certainly were giving them production stack. We weren't ready for that, but it's something we should reevaluate in the future and see what improvements have been put into that stack. Oh, I did add the picture. So you asked about the architecture. I forgot. I realized it could have been here. It's a smaller one over on the right. But you can see where the NICs are connected via the PCI switch that's in purple. And so you can see how that's connected for everything. So when you're lining things up, this will be important later. I'm going to get to a test where I'm running 8 threads on each system. We try and align, we do align the GPU communications to those NICs and make sure that they're separated and do not go across the QPI. And this is the last thing. This is, maybe we don't have as many legal disclaimers as we should at NVIDIA, but these are not intended to be benchmarks. These are not intended to be something you can go and I'm guaranteeing this is the performance you're going to get. This is just an experiment to show the kinds of things that do happen. There's certainly more work that can be done to maximize performances. So this is not any sort of guarantee to the audience. So we talked a little about NV yesterday. Just a reminder, NVLink is an energy efficient, high bandwidth path that connects GPUs and CPUs together. Current generation NVLink 1 can provide up to 160 gigabytes per second per GPU. Going into the next generation NVLink 2, which is available on Volta, that bandwidth is going to be increased up to 300 gigabytes per second.
Couple of questions. So, are there any counters available to measure the amount of traffic going on the NVLink, like as part of the NVIDIA performance counter suite?
So the question is, are there counters available on the NVLink to monitor traffic? Is that, or are you asking
Yes.
more than that? Yes. Yesterday I showed some ways with the NVML library that you can pull some counters, at least for transfer rates. You can get counts of bits going in both directions.
Second question is, can we measure the amount of power being used by NVLink to transfer it? Have the counters for that?
I haven't seen those. So the question was, are there counters really making the comment being energy efficient? Are there counters within the chip for providing measurements of energy usage? And I said, I do not know of any. So for Intel-based systems, they can connect the GPUs and the GPUs together. We have no links into the CPU yet. IBM has adopted this, though, for their CPU. You've seen them on the Minsky systems for Power 8. There's been talk about Summit already today, and that using Power 9 and GPUs, they'll be using connecting the CPUs to the GPU to provide a lot more bandwidth between the CPU and the GPU to help when you have serial portions of your code or just have to move data back and forth quickly. So the NVLink is not a limited architecture. There's lots of different ways you can put it together. For example, if you were to buy a white box based on a Supermicro architecture, you're going to have an NVLink that looks like we have up here. The black represents PCI Express, green represents the NVLink, and the blue represents the QPI. So you have 2 GPUs on one side connected to one CPU across PCI Express. You've got 2 GPUs to the other one. The wider lines between them represent multiple NVLinks. And so transparently, the links will be used together for you based on the peer-to-peer protocol. And so if you're transferring an example from GPU 1 to GPU 2, you would realize 80 gigabytes per second, in theory, protocol overheads and efficiencies, that'll probably come down to about 72, but that's what you should see. The Minsky box on the right, IBM took a different approach with that. Since they have a much higher bandwidth between the CPUs and they don't have the limitations of the QPI, they didn't have to worry about connecting the GPUs from each side together. So they used multiple links. They have 2 links between each of the GPUs and 2 links from the GPU to the CPU. So the CPU, in theory, can push 80 gigabytes per second in one direction simultaneously, 160 bidirectional between those. And so they went with a different architecture because they could leverage the CPU connectivity. The system we're going to be working with today looks like this. It's got 4 GPUs. I've redrawn that other picture a little bit bigger. 4 GPUs, PCI Express is connected. It's a hypercube mesh, so you've got 4 GPUs on one side all connected together and 1 connection back to the other side. And so not all the GPUs can communicate over the NVLink, but we'll show how that affects communications when using traditional or typical OSU benchmarks. All right, so multi-rail. This is just, I'm being honest, this is geeking out. Like, hey, multi-rail, doesn't that sound like fun? It may not be practical. I've tried to illustrate why it's practical in these sorts of information in environments. So here are the results from the bandwidth test, OSU multi-rail. I'm going to say that no tuning was done on this, and then I'm going to clarify that I was wrong. When you look at this, you can see that they overlap each other till about 256K packet size. that would mean to me that there's some sort of threshold there telling me that's when the multi-rail kicks in from some of the optimizations built in to make sure that keep latency for smaller messages as low as possible. Then you're seeing about 12 gigabytes per second for single rail. You're seeing something close to 24 for 3 of them, and you're up around 41 or 42 for 4 rails. So that it's relatively efficient. It worked well. I was very happy when I saw this result. The dip that you see around 16K on the quad rail one, Y quad rail, that's when you start pushing stuff over the QPI to communicate with the other side, and there's some inefficiencies there. I didn't figure out exactly what tuning we could change there because it does catch up, but that's what's going on. The question is, I was just going to claim single rail limit at 256K, but then I looked at some other results. Shriram Putluri, who came from this group, who works at NVIDIA, was showing completely different numbers than I was, and I thought mine were better at the higher bandwidth rate. And in the end, we looked closer, and when I said I didn't tune anything, that's not true. I was setting the the GDR copy library path, just because I was using the same setup script for all of my tests. But why should that matter? Because it's supposed to be host to host. It shouldn't be used. Well, something in the path is using that, and 1, causing it not to kick into multi-rail, and 2, actually improving performance at the end. And I talked to Ahmed about this, and it's kind of known as a problem, and it's being worked on, and this is why maybe testing with 2.3 would have been a better choice. So it's being worked on, but in a nutshell, the whole summary is still good. Quad rail network efficiency is still relatively high. There's tuning to be done, but the efficiency is very high, and we can get close to theoretical maximum with these. And go ahead. And then, so when I put Sriram's numbers back in, that's the cyan line that I just added. So those are the ones with absolutely no tuning where he just ran a command line. So go ahead. So I think the question is, okay, so what I did is I did 1 thread to 1 thread. So 2 MPI ranks, 2 nodes. This is what you get. But what does it mean for GPUs? Like, what does it mean? Because you wouldn't use that as a layout, and that's a very good leading question, because that's what I'm about to show.
I think the question was why stop at 4 megs?
Oh, stopping at 4 gigs?
Yeah.
Because that's where the test was defaulting to, and that's just where I stopped.
I'm just curious whether it drop further a gig with its storage, right? To sustain bandwidth.
Right, I don't know. I mean, and here we still see a little bit of increase going on. Is there a point, though, where it would taper off? I'm thinking no right now, because this is still just host to host. This isn't GPU to GPU. And some of the numbers you had yesterday where it tailed off, I've seen some of that too before I finished tuning. So let's see if I can address that. But for the host to host, I don't believe it's going to fall off until you get to some really large packet size that it starts to break down. And lastly, so the completely untuned one, where not my fake untuned one, because I actually set a variable, is the green line. And so you see that it caps out at about 38 gigabytes per second, but the multi-rail kicks in much sooner, which I think would be of actual benefit when doing this. But the point is, as I thought I was asking a question, is like, this is probably not, and bidirectional bandwidth, because we can, peaks out at about 77 gigabytes per second bidirectional from the single rank. So it not as efficient as the other side, but it's still pretty darn good that you can realize 77 gigabytes per second bidirectional from two ranks across 2 nodes using forward links. So what I was misinterpreting the question was, you're probably never going to run it this way. Yes, you could have an open MPI, you could have your MPI rank that controlled multiple GPUs or multiple CPUs in the case of just a OpenMP kind of hybrid code. But even when doing in most cases, I would certainly recommend my users from my previous life that if they're going to be doing hybrid codes, make an MPI rank no larger than a socket. Have it sit on the socket, because you don't want to have to be dealing with shared memory, touching shared memory across the QPI. It makes more sense for those things to lay out, even if you're only doing 1 interconnect. That's how you lay it out. But for a GPU application on a system like this, what you're probably going to do is you're going to have 8 ranks, 1 GPU per rank. That's probably going to be the layout. So a better test with this is using the MBW-MR test, where we can have n divided by 2 on one node, n divided by 2 on the other, and they're going to communicate together, and then see what the maximum performance is from that. So this is a more realistic way of doing it. And so what we have here is we have 4 cases here. We have a host-to-host transfer where I set no affinity settings. And then I redid that with pinning affinity hard so that each rank on a host represents what a GPU would do, and then it would communicate via the closest INFINIBAND card. And then Shriram gave me a version of the code. This is one of the benchmarks as of 5.3.2 that does not support device-to-device copies. And so he gave me a version of the code that he wrote that allowed us to do device-to-device so we could see what it would be really like with GPUs. And so when we tune the variables, which I'll get to in a second, we make sure affinity is set, and then we look at and we compare the blue line, which is the best you can do with host-to-host, and the best you can do with device-to-device in green. You see after about 32K that we're maxing out the INFINIBAND links. So I think that's a good result, that already, even with the existing tuning that I could accomplish, is that I can max out the network that is already there. And if you look closely at this one, that maxes out at about 47 gigabytes per second in one direction. That's better than the previous test I showed where it was on the order of 41 or 42 gigabytes per second. So not having a single thread trying to send it all, having them pinned properly, is a better way to extract performance from the network. And over here, just in this section, some affinity and tuning caused the areas you see here from on the order of 8K up to about 128K. So I went through. My goal of showing the multi-rail was just to show the benefits of or show the ability of what multi-rail can do today. But then I got into the tuning stuff, and I'm like, oh well, let's try and fix it. And this is also useful for a customer that I have that has a new GPU cluster. They're trying to run. They've been spending years taking flat memory execution profile codes, weather and climate, trying to port those to GPUs, so they don't get to leverage libraries. They have to do everything manually. They are advanced in knowing what they're doing, but now they finally bought a big system, and they're having performance issues, and so I've been trying to help them out. And this is where I went through some of the options that I found for me in these settings for the micro benchmarks that work. Again, your mileage may vary. There's certainly things that have changed in 2.3 that need to be revisited. But so when you talk about like the CUDA IPC threshold, when I saw it was 32K, I'm thinking, okay, you try a little bit on one side, a little bit on the other. Well, I found that you could see there was a dip at 32K, and going to 256K seemed to be the best value. The GDR copy limit, again, that was 4x larger. GPUDIRECT limit, as well as the GPUDIRECT receive limit. Yeah, we cranked those up as high as we can. It just happened. It worked. It gave us a lot better performance at the tail end. A lot of the communications you could see within the other tests, and we'll see in the next set of tests. So that one was kind of interesting. That there was no value too small that wouldn't improve performance. And then at one point, I started getting nervous when I was doing all this testing that I found that going down a certain path of tuning would change. You want different parameters to tune between intra-host and inter-host, depending on what was going on, and that made me nervous because you can't do that yet. And we've talked, and that's a work in progress. But for example, when we cranked GPUDIRECT limit up really high, that caused problems other places. But by setting SMP GDR to 0, that kind of corrected it. And so that was nice from the micro benchmark perspective. And again, the search space wasn't exhaustive. There's certainly more work that can be done here. All right, so that was all INTRANODE. And so I wanted to show kind of what's going on with INTRANODE on an Intel-based 8-way GPU system with NVLink. Some of the results showed from the power today, showed a little bit of the NVLink performance. I'll just go into how it relates to what we're seeing with the Intel side. So I did 3 comparisons, or 3 test cases. One is GPU 0 to GPU 1. They are connected by NVLink, and they're connected on the same PCI Express switch. So they are as close as you can get. GPU 0 and 4 are still connected by NVLink, but they're on a different CPU socket. So when you can't use NVLink for some reason, then you're going to have the problem going across the QPI. And then for 0 and 6, how much time do I have left? 5? Okay, 5? Okay, that's perfect. And then for GPU 0 and 6, it's not NVLink connected, nor is it connected via PCI Express. It has to go over the QPI. So that's a worst case scenario. Certainly, you could do all the permutations, but this kind of represents the 3 sorts of communication patterns that you're going to see across an architecture like this. when doing device to device, there's definitely some tuning that was an advantage to us. So this is the case where we're doing GPU 0 to 1, device to device. We've got the case where I just used the defaults out of the box. Then I set the affinity, and then I did the fully tuned case with the values you saw before. Again, in the 1K to 256K is where you start to get some improvements, but they seem to overlap. One thing you can see here is that the maximum bandwidth you see here is about 17 gigabytes per second. That clearly is not over PCI Express. That is over NVLink. So you can realize that bandwidth pretty easily. With out-of-the-box code, you don't have to make any modifications. When we are, and then I'm skipping the 04. This is just to show the 06. They kind of overlap as well. I think there's some more tuning that we're going to be able to do here. You start to see them improving with tuned, but once we hit about, I think that's 8K, we lose whatever's going on, and we need to work out those issues. This is where it gets a little interesting. This is where the tuning got creative, and I certainly didn't go through all the exhaustive permutations on this one, because I hope that when you're transferring data in a GPU application, you're going device to device, because the goal is to keep your application on the device as much as possible. Anytime you have to go through the host, you're going to hit performance penalties. So I showed the differences with device to host and host to device transfers because the benchmarks will allow you to do that. It comes up with some curious performance characteristics, and I hope you never have to do that. But again, there's no performance. So for going, you can see in the red line, that's our NVLink connected communication. That's 17 gigabytes per second. Great. But when you start going to the host, you can no longer use the NVLink. Therefore, it has to go over the PCI Express no matter what. And device to host and host device certainly are much lower with some issues. When we tune, we move everything up. That was good. I certainly would like a better curve than that, but there's certainly some improvements there that were beneficial. So 0 to 4, you get a little bit different characteristic because you're going across the QPI now. Visually, I was plotting things in 3 dimensions for how this all worked, so it's hard for me to pick the right plots. As we tune this one, you can see a definite improvement of bandwidth both over the NVLink and the hosted device and device to host transfers, which is useful. And then finally, we have no NVLink here, so this is what it looks like with defaults and moving on to the transfers. Maximums didn't change too much, but it was in that, I think, the critical section of 4K to 128K that we see some improvement there. So there's some good stuff there as well. I'm going to skip those because I think I've run out of time already. I didn't show any latencies on this. When I'm starting to talk about NVLink, the key is to minimize, keeping the latencies low, and the way you use that in the MVAPISH 2 stack, which is one of the reasons I really like it, is using loopback with the IB. And when it's trying to optimize small messages and for latency, it's going to use loopback over IB. That's why all these are the same, even if there's NVLink involved. And so you don't really see much there. My goal was really bandwidth, but bandwidth and latency are kind of inverted. But this is very useful, but it doesn't show off NVLink. It's not something you need to worry about at the small message size. So summary is, MVAPISH 2 is already very efficient with dual rail and quad rail configurations as measured by OSU benchmarks. Affinity, I didn't talk about it much. I think it's preaching to the choir. We should all know it, but the better it's very important to know exactly what's going on and set that correctly. The tunables help a lot, and the values of the tunable can change dramatically. It's not just small changes. They can be drastically different based on your architectures, in this case P100s and NVLink. And I think you've already talked about some really good work in future products to more optimize that process. And for my customer, I'm going to go now and download Tube 3A and redo all of this and see what else I can help them with to see where there's improvements there for their specific architecture.